So today we're going to look at optical isomerism. Now within stereoisomerism में दो किस्में हम लोग पढ़ते हैं. The first one was cis-trans isomerism, okay, which is a subset of geometric isomerism, okay, and then the second type of isomerism that we study is, okay, the second type of isomerism that we study is optical isomerism. Okay, optical isomerism. Now, what is optical isomerism? Optical isomerism, okay, arises when a molecule has what we call a chiral, center. Now, what exactly is a chiral center? A chiral center is also known as a chiral carbon atom. It is also known as a chiral carbon atom. Okay, now what is chirality, or what is a chiral carbon atom? A chiral carbon atom, okay, a chiral carbon atom is this, okay, it is an sp3 carbon, okay, an sp3 hybridized carbon. In other words, it makes 4 different bonds, or bonds to 4 different atoms, okay, and it's an sp3 carbon that is bonded to 4 different atoms or groups of atoms. 4 different atoms or groups of atoms. All right. Let's look at an example. Let's say you have this molecule here. Okay. So you have this molecule. All right. Now over here you notice that this carbon atom is bonded to 4 different atoms or groups of atoms. Okay, this is known as a chiral carbon. Okay, now why is this a chiral carbon? Because again, it's bonded to a chlorine, a hydrogen, an OH, and a CH3. So if you were to represent it in 3 dimensions, right, this is what this would look like. We draw the tetrahedral structure for the carbon. Okay, this is how you would represent chiral compounds. It doesn't matter which group you put where. Okay, let's put the H on top here. Then you have a CH3, you have an OH, and you have a Cl. So now what we have over here is, okay, if you take this compound here, this compound over here, okay, and here we have the chiral center. Usually we use a star to denote the chiral center. Okay, you have a mirror plane. This is called a mirror plane. Okay, this is just a representation. Okay, and if you take the mirror image of this, this is what you get. Right? Again, whatever's closer to the mirror will appear closer on this side. Right? This is on the front and further away, so that will appear again on the front, on the other side. Right? So it will look like this. Right? You have the Cl at the back, again on the far side, so it will appear like this, and then you have the hydrogen atom on top. Okay. Now, one way to identify that these two are different. Okay, the one way to identify that these two are different is this. If let's say you've aligned the 2 hydrogen atoms on top, right? And now let's just pick an order. Let's say that I'm going to go from Cl to OH to CH3. Those are the 3 different groups that are bonded, right? मैंने hydrogen atom को top पे रख दिया. This is just an example of how you can identify chiral centers. Okay. Now if you go Cl, OH, CH3, hydrogen atoms दोनों top पे. If you go Cl, OH, CH3, you're going in the counterclockwise direction here. And over here, if you go Cl to OH and then CH3, you're going in the clockwise direction. So these are essentially left and right-handed isomers of each other. This one is counterclockwise. This is just an example. Just pick any order. So let's say you pick this order. You can go OH, Cl, CH3. जो भी आप order pick करो, आप देखोगे, आप दो को ऊपर same रख लो, और नीचे वाले 3 जब आप देखोगे कि वो डिफरेंट ऑर्डर में जा रहे हैं. यहाँ पर they're going counterclockwise, यहाँ पर they're going clockwise. So these are actually not the same molecule. Okay, these are not the same molecule. Try rotating this 180 degrees. If you, let's say you rotate it 180 degrees like this on the vertical axis like this, okay, what will happen? If you rotate it 180 degrees, this is what you'll get. You'll say, okay yaar, you know what, अगर मैं rotate करूँगा फिर तो दोनों CH3 एक ही साइड पे आ जाएंगे, फिर तो सेम चीज़ आ जाएगी. लेकिन अब क्या हो जाएगा, आप इसको रोटेट करेंगे तो फिर Cl जो पीछे की तरफ है वो आगे की तरफ आ जाएगा, और जो आगे की तरफ है वो पीछे की तरफ चला जाएगा. सो अगेन दे आर नॉट द सेम, राइट. यहाँ पर अब OH आ गए, यहाँ पर OH पीछे. सो नो मैटर व्हाट you do, these two are different compounds. Okay, these two are different compounds, and these are called enantiomers. They are a special type of optical isomers. Okay, these are called enantiomers. Enantiomers are specifically known as, enantiomers are defined as, they're defined as non-superimposable. Okay, non-superimposable means non-identical. Okay, you can't overlap one on the other, so they're non-superimposable mirror images of each other. This carbon atom over here, okay, this is a chiral carbon. All right. The question that I have here is this, okay? How many isomeric aldehydes, okay, have the molecular formula C5H10O. Again, this is a question from your past papers. Okay. All right. So now again, the question is saying how many isomeric aldehydes have the molecular formula C5H10O. Now that means over here we already have a C double bond O. Okay, CHO group, that's the aldehyde. बाकी सारे single bonds होंगे, right? Because से 12 से 10 हो गए hydrogen atoms. So here, one structure that you have is this. One structure that you have is CH2, CH3, sorry, CH2, CH2, and then CH2, CHO. Right? That's one possible structure. That's the straight chain. The other possible structure that you have is this. You can also have branching. So here you have a 5-carbon chain. Again, the way to do this is to draw all the structural isomers. So you start with a 5-carbon chain. Okay, then you say, okay, what if I had a 4-carbon chain? Okay, in a 4-carbon chain, I'd have something like this. Right, now I can have branching on 2 possible places. I can have it on this carbon, or I can have it on this carbon over here. Right, so let's say now over here I have a branch over here, let's say, right, CH3, and then I have a CH2 and I have a CH here. Right, this is one possible 4-carbon chain. The other possible 4-carbon chain that I have is if I have branching on the 2nd carbon like this. I can have a branch over here as well. Right? This methyl group over here can branch on carbon number 2 or carbon number 3. This is 2-methylbutanal, this is 3-methylbutanal. This is just pentanal, right? So 4-carbon chain में भी मेरे पास ये possibility है. So ये CH3, then I have CH2, CH over here and a CH3. Okay. So these are my only 2 possibilities for a 4-carbon chain. Okay. Another possibility that I have is a 3-carbon chain. Okay. 3-carbon chain में क्या है मेरे पास? I have something like this. I have this CHO, right? And then I have a carbon here and a carbon here. right? So these are my four possible structural isomers. Okay, these are my four possible structural isomers. Now, do any of these structural isomers show stereoisomerism? अब यहाँ cis trans तो नहीं है obviously because there's no carbon-carbon double bond. So now we're looking at optical isomerism. Do any of them have a chiral center? Now, obviously, anytime two identical hydrogen atoms are bonded, it's not a chiral center because a carbon has to be bonded to four different atoms or groups. यहाँ पर this carbon is bonded to two identical methyl groups. So again, it's not a chiral center. What about this carbon? It's bonded to a hydrogen, a methyl, an ethyl, and an aldehyde group. Can I say that this is a chiral carbon? Draw the tetrahedral structure here. Let's see. Let's take this star over here and let's try to draw out a structure. If you notice, this carbon over here is bonded to an ethyl group, CH2CH3. It's bonded to a methyl group, which is a CH3. It's bonded to a hydrogen atom and it's bonded to a CHO. Can you see that? This carbon here is bonded to an H, a CH3, a CH2, CH3 and a CHO. So this, is it bonded to four different atoms or groups of atoms? So again, these are CH2, CH3 and CH3 are different groups here. So this carbon over here is clearly bonded to four different atoms or groups of atoms. So this particular structure has two different optical isomers. So this structure actually represents two different molecules. Okay, you have this isomer. So over here, again, this particular structural isomer, okay, exists as a mixture of, or can exist as a mixture of optical isomers. There are two possible optical isomers. Okay. Again, you have to clearly show that the carbon is bonded to this carbon, okay, and you can show again जो भी group top पे आप उसको वापस top पे लिख दें, okay, यहाँ पर जो आ रहा है इस तरह से CH3 and then you have the hydrogen atom at the back. So these are actually two different, this structural formula actually represents two different molecules. It could be this one or it could be this one, right? Again, if you just arbitrarily see over here, if you go aldehyde to methyl to hydrogen, over here you will go clockwise, here you will go anti-clockwise. So they're two different molecules. So this, यहाँ 5 carbon chain में you just have one possibility, 4 carbon chain में you have one possibility here, but this is actually two different optical isomers, and 3 carbon chain में you have one. So your total number of isomeric aldehydes is 5. All right. The next question that I have is this. How many isomeric alcohols, okay, have the molecular formula C3H7ClO. All right. So because you have a 3 carbon chain, you don't have any chain isomerism possible. Okay. For that you need at least 4 carbons. So we're going to look at position isomer. So let's say that I have OH in position 1. Okay. So OH is position 1. Okay. How many possibilities do I have there? Well, if I have this OH in position 1, right, the chlorine can be on position 1. The chlorine can also be on position number 2, right? And the chlorine can also be on position number 3, right? Like that. Sorry. So OH is on position 1 and the chlorine is on position 3. Right? So these are 3 different structural isomers I have with just the OH group on position number 1. Okay. Now if you notice, okay, I'm going to write this down. and we have a CH3 here, we have a CH2, a CH2, and a CH2 at the end, right? Now over here, if you notice, we have a chiral center in this compound. This carbon is bonded to an ethyl group, an OH, an H, and a Cl. So it exists as a mixture of optical isomers, right? This particular structural formula can be one of two possible optical isomers, right? So we will, just for practice, we're going to draw out these isomers as well, okay? But now I'm going to show it slightly differently, in the sense that I'm going to show this closer to the mirror plane like this. OH, you have a Cl, you have a CH2, CH3, and you have a H. और इसका mirror image क्या होगा? Like this. Okay, you have a CH2, CH3. Okay, so this particular compound, this particular structure actually exists as a mixture of optical isomers. So over here we can clearly see that this particular structure represents two different compounds, right? It can represent this optical isomer or this optical isomer. They're two different things. Exact same thing here. Exact same thing here. This is a chiral carbon. Okay, if you notice this carbon is bonded to a Cl. Okay, it's bonded to a Cl. It's bonded to an H. It's bonded to a CH3, and it's bonded to a CH2OH. So this carbon is bonded to four different things, right? H, Cl, CH3, and CH2OH. So this carbon again is bonded to four different atoms or groups of atoms. So it has this is a chiral center. So again, this particular structure could be one of two possible optical isomers. Okay, so again, this particular structure represents two different molecules. Okay, and then the last one doesn't have a chiral center, so there's only one possibility here. Okay, so with just in OH position 1, you have 5 different possibilities. Alright, so here we had OH in position 1. What if we had OH in position 2? Okay, so let me just draw sort of a line here. What if you had the OH in position 2? Obviously, OH can't go to position number 3, because that will just become position 1. Okay, so OH in position 1 or OH in position 2. Now, if you had OH in position 2, then what do you have? Well, you have the OH in the middle, right? And now the chlorine can go either on the same middle one. The chlorine can either go on the middle one, okay, or it can go on one of the ends. Doesn't matter which one, because again, it will be on the first carbon. यहाँ पर जाएगा, यहाँ पर जाए, it's the same thing, right? So these are your two different positions where the chlorine can go. So now what you have here is you have a CH3 and a CH3, and here you have a CH2, and here you have a CH and a CH3. Now again, if you notice, the one on the left doesn't have a chiral center. It's bonded to two identical methyl groups, so it won't show chirality. But this one, this carbon here, is a chiral carbon. This carbon here is a chiral carbon. It's bonded to a hydrogen, an OH, a CH3, and a CH2Cl, which is different from a CH3. So again, you have a chiral carbon here. So this particular structure can represent two possible optical isomers, right? This is just an example of how I've drawn them, but you can draw these ones in a similar way, okay? And obviously this particular structure just represents one particular isomer because it doesn't show stereoisomerism, okay? So over here, your total number of isomers is actually 8, okay? Total number of isomers is actually 8 because you have a total of 1, 2, 3, 4, 5 structural isomers, but 3 of those structural isomers show stereoisomerism. More specifically, they all have chiral centers, so they show optical isomerism. Okay? That's your answer. Now, if you look over here, chiral centers जो होते हैं आपके, okay, like this is a mixture of optical isomers, right? Now, chiral centers, okay, if we notice, as I mentioned in class before, okay, chiral centers are asymmetric. Okay, chiral centers are asymmetric. Okay, so what we see over here is that they're not symmetric. The reason, this is why the mirror images are different from each other. If there was a line of symmetry, if you look at this carbon atom, No matter where you draw a line of symmetry, there will never be a line of symmetry here. There are 0 lines of symmetry on a chiral carbon. Okay? So if you draw a line of symmetry through the chiral carbon, in any direction, you'll never get a line of symmetry. If you attempt to draw a line of symmetry, you'll never get one. Okay? So that's what we notice over here. And this asymmetry is only possible again if 4 different atoms or groups are bonded to the carbon atom. All right, and this will help us identifying chiral carbons in rings. This will help us identify chiral carbons in rings. So if you look at chiral carbons in rings. Okay. Now, let's take an example. Let's say I've drawn this molecule here. All right, so normally this is a very common type of question in the exam where they give you like a big molecule with a skeletal formula in rings, and you have to identify the chiral centers here. So over here again, this is a chiral center. Okay, the reason why is because this carbon is bonded to 3 different carbons and it's bonded to a hydrogen. So that's 4 different groups, and we can clearly see that there is no line of symmetry. Right, there is no line of symmetry here. So in other words, we have a chiral center. Okay, it's asymmetric left and right. Right side पे बराबर वाले carbon पे OH है, अगर left side से देखें तो पूरा घूम के OH आ रहा है. Okay, so that's one chiral carbon. Are there any other chiral carbons here? Again, if you notice here, okay, what we have over here is, if you look at this OH bond, this OH over here, again, it's asymmetric with respect to this carbon atom. The reason why is because इसके बराबर वाले पे methyl है, again यहाँ पर बराबर वाले पे methyl नहीं है. So these are 2 different groups. So this carbon is bonded to an OH and H and 2 different groups over here, right? So that's a total of 4 different groups. So this is also a chiral center. So there are 2 chiral centers in this molecule. All the remaining carbons are CH2s, right? इस पे 2 hydrogens हैं, इस पे 2 hydrogens हैं, इस पे 2 hydrogens, इस पे 2 hydrogens, और ये CH3 है. So जहाँ पर भी obviously identical hydrogen atoms आ गए, you have more than one of the same group. That's when you can't have a chiral center. So when we talk about the physical and chemical properties of isomers, okay. So when it comes to structural isomers, okay, structural isomers may have different chemical and physical properties, right? So for example, functional group isomers have different chemical properties as well as physical properties, right? Like esters and carboxylic acids can be structural isomers of each other, but they're very different in terms of their chemistry. Okay, so chemical properties usually आपको कहाँ मिलती है? Functional group isomers. Okay, and physical properties भी obviously फर्क हो सकती हैं जिस तरह से, again, अगर आप carboxylic acid और let's say ester को compare करो, carboxylic acid can hydrogen bond, esters can't, right? Some alkanes that are more branched versus straight chain alkanes के melting points and boiling points में फर्क होता है, right? Branched alkanes have lower melting points and boiling points, and so on. Okay. Then when we talked about stereoisomers, you have cistrons, okay, and you have optical. Cistrons isomers usually have similar chemical but different physical properties. Right? An example of this, a very simple example would be this. So for example, like this, let's say, I'll draw a very simple example. right? Now this molecule over here is polar, right? There's a net dipole towards the chlorine atoms, right? It's a polar molecule. In other words, it'll have a higher melting point and boiling point than इसका stereoisomer. इसका अगर आप cis trans isomer देखें, something like this, right? यहाँ पर if you notice, the dipoles are in opposite directions, so they'll cancel each other out. So this is an example of two molecules that are cis trans isomers of each other, okay? That because one is polar, the other is non-polar, they're going to have, the polar one will have a higher melting point and boiling point, for example, than the non-polar one. All right. Okay. So this is an example of two cis trans isomers, one being polar and the other being non-polar. So they can have different physical properties. Okay. Optical isomers, on the other hand, have identical or similar chemical and physical properties. Okay. As I mentioned, the only time that chemical property can vary is if it's in a stereoselective system. In a system where 3D shape matters, the 3D orientation of the groups matters. Otherwise, in a lab, if you're reacting with chemical reagents, optical isomers will show no difference, okay, in the way they react. The only difference in optical isomers, the only difference is the difference is in the direction, okay, in which they rotate plane polarized light. Plane polarized light. This difference in the direction of plane polarization is specific to what we call enantiomers. Enantiomers. Okay. So basically, जो mirror images होते हैं एक दूसरे के, non-superimposable mirror images, okay, they rotate plane polarized light in different directions.